right. All right. Hi everyone. All right. I like the Hunger Games over here. There's fewer and fewer people. It's anyway. Okay. Is Math Lab tomorrow or something, or when is it?
Like Sunday.
Bridge. Okay. Well, bridge. Fine. Okay. All right. Okay. So we Sunday. Okay. Yeah. And now I mean I mean like I kind of also do Sunday due dates, I suppose, except mine are like unofficial. So yeah. But well, because like I like give the grace days, whatever. So okay, all right. So bridge or no bridge, we're gonna keep going. So okay. So where we stopped last time, so we are doing recursion. So for the people who weren't there, just like, so like you can't push on a rope. So that would be what recursive step. I'll just redo the example quickly and we'll start up debugging what we haven't done before. So what else? Sorry, you can't push on a rope is actually the base case. And then to get the answer, you must know the answer. And that is the step. And the third rule today is bridge is due Sunday. Okay. So, okay, all right. So let's redo where we left off yesterday. So what we're doing was computing x to the n, and we were doing, so this is called the repeated squaring trick. So what we're saying is that x to the n, or rather, like x to the 16, we said is like x to the 8th and then squared. And then that is itself x to the 4th whole squared. And then x to the 4th is x squared squared. So here I'll substitute x squared squared. And that's like that. And the idea is that instead of multiplying x by itself 15 times, we just multiply x by itself once, and then we multiply x squared by itself once, and then we multiply x to the 4th by itself once. So that at the end just gives us the same thing, but with 4 multiplications. And basically the formula that would work if we didn't have the issue of not everything is a power of 2 is something like this. So power fast, we said xn is equal to power fast divided by 2 and then squared. So that's kind of the basic formula, right? So you compute this and then you square it. So now we had to elaborate on it a little bit, because while this is true when n is even, when n is odd, what we need to do is we need to post multiply by x again, so that we actually get x to the n and not x to the n minus 1. Right? So this is how we wrote it. So we said power fast. I'll do the base case in a bit. So we said half power is power fast x n divided by 2. And then the basic idea is either, so like if you think about it, x to the 15, like it is equal to x to the 7.5 squared. That is true, but x to the 7.5 we can't really compute. So instead, what we do is we divide using integer division. So this would be x to the 7, and then you square, and that's x to the 14. Because of the 0.5, we're missing a factor of x, so we need to post multiply. If it's even, there is no problem. So we compute half power, and either n is odd or even. We'll take care of both situations. So we'll say if n is even, we just return half power squared. So the reason I write it like this is just like for aesthetics, right? So like I could just say half power squared, but that would be kind of cheating because the whole thing that I'm trying to do is implement power. So if I already have squared, it's kind of silly. So I'll do half power times half power. Otherwise, I'll do half power times x. So I post multiply by x because if I round down here, then I'm missing the factor of x. All right. So where we stopped kind of is we wrote the base case. So one possibility is you might naively just say, okay, if n is equal to 0, then the answer is 1. And you might think that you're done. You're not done because that produces infinite recursion. So I want to say in more detail why it is that this produces infinite recursion. So let's say that I want to compute x to the third. So I'll call power fast x3. And then what's going to happen? So this is the first time that I'm doing this kind of graphic representation, and we'll be using it a lot this lecture. So I'm calling power fast x3. So what's power fast x3? Well, I plug in the 3 here. I skip this because 3 is not equal to 0. And then I compute half power. So when I compute half power, what I'm doing is I'm calling power fast x to the n over sorry, this by the way is actually going to work. So the list is not going to work. So when I'm calling power fast, I'm calling x to the n over 2. So that means that power fast x3 is gonna call power fast x2. Sorry, 1, right? So here 3 n was 3 divided by 2, we get power fast x1. Let me check if there is an issue on Discord. Okay. Yeah. All right. So we are over here. So now what we're doing is we're calling power fast x1. So n is still not 0, so we're not returning 1. And now we're going to compute half power fast x1 divided by 2, so that's 0. So we're going to call power fast x0. So one way to think about it is when you call power fast x1, what happens is you get to this line and around for this to compute. Once this computes, you'll know what half power is inside of this call, right? So for n equals 0, we do know what this returns because this is just this. So power fast x0, well, that is just going to return 1. Right? Because power fast x0, that's straightforward. It doesn't do anything except for this. So now that we know this, we can go back and say, okay, so what happens when you call power fast x1? Well, what happens is you compute this, and this is 1, and then you return 1 times 1 times x. So that means that we know that power fast x1 is going to return x. And now we're going to say, okay, so what happens when you call power fast x3? Well, what happens when you call power fast x3 is you get to this line. We now know that this returns x. And 3 is again odd. So we're going to return x times x times x. So x cubed. So that returns x cubed. And that's the answer. So again, one way to think about it, like why does it work? Well, it works because the math is just true, right? So we just worked out that that is the correct formula for x to the n. Another way of thinking about it is we said, okay, so this we just know what it does because this is just if n equals 0, return 1. And we say, okay, fine. So we know what that does. So now we get to think about what power fast x1 does. And we can just say, well, what that does is it gets the 1 here, and then it returns 1 times 1 times x. So now we know what power fast x1 does. So then we say, okay, so what does power fast x3 does? Well, it calls power fast x1, that returns x, and then it returns x times x times x. So that's x cubed. So I think, so different people think differently about this. Like it's different, different people find different things intuitive. I think for the more complicated functions that we're going to write, thinking about it in terms of the recursive step probably makes more sense because you're just saying, well, this is the math, so we're done. Like if the math is correct, it's got to work. But you also might like to think, okay, well, like, okay, but this is the math, but how does it actually work? And the way to think about it is think from the bottom up. So once you know what this does, you know what this does. Once you know what this does, you know what this does. Make sense? All right, so that was actually the second to last example. And now I'll do what I actually promised, which is the infinite loop. So that was the sumless 2. So again, the math was that sumless 2 of L is equal to sumless 2 of L from the beginning up to halfway through the list, plus sumless 2 from halfway through the list and up to the end. So that's just the math. If you want to compute the sum of the list, one way of doing it is compute the sum of the first half, compute the sum of the second half, add those up, that's the sum of the entire list. So I'll just take this and I'll put it in the return statement. Like so. And now I'll try the thing that doesn't work. So I'll say if length of L is equal to 0, I'll say return 0. So that looks like a base case, but it's not enough of a base case. So first of all, let's try it. Well, let's fix it. Sum list. Okay, this is fine. I did not close the bracket here. All right. So that is fine. So I'll say L is equal to whatever, 1 to 5. And I'll try to print the sum. And what I get is recursion depth exceeded. So first of all, I'll see that it is what I think it is. The way I'll do it is every time I call some list, I'll just print the L over here. So now, like, I'm returning this, but also every time some list 2 is called, I'm saying, okay, like, this is the L for which I'm trying to compute the sum, and this is what I get. Eventually, it'll get tired and say, like, enough is enough. Okay. Hello. So what's going on here? Let's, again, make a picture. So I'm starting with 1 to 5. Like so. And here, what we're doing is we're saying, okay, the length of L is not 0 initially. So we're here. So in order to compute the sum less 2, I should say, of the whole thing, I need to compute this helper function call and compute this helper function call. So the way I'll draw it is I'll have 2 arrows. So I'm making a call here. So that's going to be sum less 2. And this is L up to length of L over 2. So length of L is 3 over 2 is 1. So this is just the first element. Does that make sense? Because this is up to 1, not including 1. This guy is going to be L starting from 1 and up to the end. So that's going to be the other half of the list, approximately. So that's going to be 2, 5. All right. So in order to compute this, what I need to do is I need to compute this. And I also need to compute this. Now, what do I need to do to compute this guy? Well, if I call sum list 1, what happens is the length is still not 0, the length is 1. So I need to compute this, which is sum list L from the beginning up to 0. So that's nothing. So the empty list. And then also the rest of the list, which is just the list, right? So, okay. So that's your rule to get the answer. You must know the answer. So it is true that the sum of this guy is the sum of this guy plus the sum of this guy. But what's going to happen is now I need to compute this guy again. And how that goes, we already know, right? It's both of those again. So I'll do an annoying thing where I'm copying this and I'm pasting this, and then I'll move it a little bit. So that's going to be like this again. And then this is fine. This is returning 0. But this is, again, going to produce those 2 calls. The best I can say for this is less annoying than drawing it on the blackboard, right? And that's going to go like this forever. So to compute the sum of this list, we're going to have to compute the sum of this list again, which is the same list. And we're going to have to compute the sum of this list again, and so on up to infinity. So that is why we have infinite recursion here. So how to fix it? Well, you just say if the length is 1, we'll return L at 0. If you do this, there's no problem. So if you just think about it again in those terms, then what's going to happen is this is going to call this, and this is just going to return 1, because now if the length of the list is 1, you just return the first element, so the sum. So this is fine. And then this is going to return 2 plus 5, because it's going to compute the sum of the first half, which is 2, sum of the second half, which is 5, and it's going to return 2 plus 5, so you'd be done. So there's not like a general way of keeping yourself safe from it. It's a case-by-case thing where it happens that if we just had done this as a base case, it's not enough. You just have to think it through case by case. Make sense? All right. Questions about this? Yes. Say it. Do you still need the first if statement? You could argue that you kind of don't, but you might say, well, like, what if I actually plug in the empty list? So yeah, like if you say I'm assuming that the list is not empty, then sure, like you can leave it out. So okay. All right. So that's like that. So that was just an example of avoiding infinite recursion. Let me do one more example that's going to come up in the lab and actually has to do with something that someone over here asked yesterday, which I'm leaving for the lab. And then we'll talk a little bit about the complexity of recursive functions. And that's like kind of like a fun thing. So let's say that what we want to do is print the list L. So one way of thinking about it is if you have a list, how do you print it? Well, and like assuming you want to do element by element. Well, you can kind of think about it in the same way as how do you compute the sum? Well, you first print this guy and then you print the rest. Right? So to print L at 0, and then print L starting from 1 and up to the end. Make sense? So let's do that. So that's, again, basically decomposing the problem, right? So what do I need to do to print the list? Well, print the first element, done a little bit, and then do the rest of the work. And it so happens that we can do the rest of the work by just calling print list as its own helper function. We also need a base case. So if the list is empty, there's nothing to print. So I'll just return. So that also takes care of the situation where the list is empty and I don't want to try to print L at 0 because there is no L at 0. That would produce an error, but that would never happen because if the length of L is 0, I've already returned. So there's definitely an L at 0, so there's no problem. Make sense? Okay, let's try it. Make sense? So I'll draw the call tree in a second, but I now want to do a somewhat different problem. So let's say that I want to print the list L in reverse. So how do we print the list L in reverse? Well, yeah.
I think like what's passed in is a list of a list, so it would just print the first element, or is that meant to be like just when you do a list?
No, so here what I'm so the like this is correct. So here what I'm doing, it's not like a list of the list. This is like L1 to the end. So this is I see what you mean. Yeah. Okay, thank you. Yeah. Thank you. Yeah. It still works. Anyway, thank you. So print the list L in reverse. So how do you print the list L in reverse? Well, there's multiple ways. You could say, well, to print the list L in reverse, like first print the last element and then print this. That would work, but I want to do it another way. I want to say, well, how do you print L in reverse? Well, the last thing that you want to print is L at 0. So I'll write it as like, then print L at 0. If you think about it, what you can do is you can say, okay, I'll print 5 at the end. And then I'll also print this in reverse. So I'll print like 20 and then 125 and then 2 and then 10. And then at the end, I'll print 5. Does that make sense? So I'll say it as print L1 to the end in reverse. And then print L at 0. Does that make sense? So this is just mathematically, this makes sense, right? So print 125, 2, 10, 5, and then print 20. That's printing the list in reverse. And the nice thing is that I can actually take this and modify it a little bit. And get the code. So to print the list L in reverse, we print L1 through everything in reverse. So this is this guy. And then we print L at 0. But another way of thinking about it is all I did is I changed the order of those lines. So let me first do it like this, just to make sure it works. And that's like this. And indeed, we printed, 20, 125, 2, 10, 5. Informally, why did it work? Well, because we call print list reverse with L. And what happens is we print this in reverse. Printing this in reverse just means print 125 to 10, 5, assuming that the concept works. And then we print 20. And that's what we did. Right? So, okay. Sorry, and then we print 5, of course. So, okay. So let's now draw, so this is called a call tree. This is like the diagram of the calls. So what happens here? So with print list, I'm calling it like this. I'll make it a little bit shorter so that it's not as boring. And then I print L at 0, so here it's going to say print 5. So I'm doing this. And then I'm saying print list the rest. So that means that I'm calling print list with 10 2. When I'm calling print list with 10 2, what happens? Well, 10 gets printed. And then I'm saying print list with just 2. Here, 2 gets printed. And then I call print list with the empty list. What happens here is nothing. So the process was we printed 5, then we printed 10, then we printed 2. The whole list got printed. Another way of thinking about it is if you say print list, the empty list, that will just print nothing. If you say print list 2, it'll print 2, this guy, and then it'll print nothing. So that works. If you say this, it'll print 10, and then it'll do this, which prints 2. So that works. And similarly, this works. Make sense? So now let's think about this guy. I'm copying and pasting this. So when I'm calling print list reverse, what happens? So I'm over here, I called it here, and I'm saying print list reverse on this guy, right? So nothing got printed yet, because in order to print list reverse this, I need to call this, and I'm still waiting around for it to be done. I'm then calling print list reverse with 2. And again, when I call print list reverse with 2, I get to here, nothing is printed yet. I'm waiting around for the empty list to get printed. When the empty list gets printed, which means nothing happens, then I say, okay, when I call this, what happened is this, nothing, and then 2 gets printed. So this is going to be print 2. When I call it like this, what happens is first this happens, this prints 2, like we just said, and then 10 gets printed. When we call this, what happens is first this happens, and we know that this prints to 10. We already worked it out. And then 5 gets printed. So you'll notice that the picture is exactly the same. The order in which things happened is different. The reason the order in which things happened is different is here I'm first waiting around for everything to be done, and then I'm printing L at 0. Over here, I'm first printing L at 0, and then I'm waiting around for things to be done. So one way to think about it is it's just a curiosity. Like it so happens that if you switch those lines, it works out. Another way of thinking about it is this is just the recursive step. The recursive step is if you are wanting to print the entire list forward, you print 5, and then you print the rest of the list. This is this. If you want to print the list in reverse, you want to print the rest of the list in reverse first, and then you want to print the first element. And this is what this does. Right? So this gets to be more complicated. I personally don't think I have like in my mind like why this works. I just believe it does. So people sometimes refer to this as kind of the leap of faith. So I'm just saying, like, I set up print list reverse. It's the function that prints the input in reverse. You know, trust that it works. And then, well, I'm using a helper function. I wrote it myself, so it's got to be good. So I'm just using it. And that's the more usual way of thinking about kind of more complicated recursive functions. You just say, okay, I trust the math. So it's got to work. You can, of course, work out why it works in every particular case. Make sense? All right. Questions about this? Okay. All right. So we have a few minutes left. So should we start complexity? I don't think we should start complexity. I think we should just go because there's not very many people left. So I'll just let you work on the bridge. But okay, Friday we'll do a serious lecture until the end. See ya. Bye.